Now, as we further develop our understanding of the functional anatomy portion of the class, we're going to understand the different structures and materials and how these materials and structures respond differently to loads or lack thereof throughout everyday life and different activities. So the focus of this presentation will be to investigate the different structural components and their makeup, as these are key elements in the movement of the human body. Those structures are going to be the skeletal muscle, the skeleton themselves, and the nervous system. One of the major questions that arise when we begin to analyze sport and human movement is whether or not athletes choose the sport or whether the sport chooses the athlete. We can look at the different sizes of a basketball player and a volleyball athlete compared to the gymnast, or further identify differences in their body types of sprinters and endurance runners. And additionally, we can look at the long torso of a swimmer compared to the typical torso of a non-athlete as evidence of, do we choose that sport or does the sport choose us? The body type and frame differences continue to be shown when looking at a road cyclist versus a sprinter or criterion cyclist. We then can move to more focusing on different athletes and an elite level of a specific sport like golf. In this case, we have Tiger Woods and Phil Mickelson, both extremely successful. However, their bodies are quite different from a structural standpoint and a functional standpoint. Or from an individual athlete like Tiger Woods, who has injuries and changes his swing pattern multiple times. And we can look at this from both a structural and function. These angles here drawn are going to be some kinematic analysis we use later on down the line. There are many different athletes that are designed to play different sports at an elite level. And each sport represents a different body type. If you think about a volleyball player or a basketball player, it's a different body type than if you think about the gymnast. And that's just something that you to think about. Think about different runners, different cyclists, different football players. Each football position is a different body type. To begin the conversation regarding the anatomical considerations, we begin with the skeletal system. And we understand that there are 5 major functions that may be associated with the skeletal system, but for our purposes, we're going to focus on the 2 that are important for human motion, those of leverage and support. There are a number of structural shapes that bones have evolved into based on the function and stress by which they are introduced. Long bones are typically involved in both support and shock absorption while providing levers of muscular attachment. Bones like the pelvic girdle are responsible for protection and attachment. There are other specialized bones of the spine and patella that have special functions, from attachment angle to protective and attachment sites. These are particular bones, long bones of the foot and the lower leg and the femur, all involved with leverage support, attachment sites, movement. We go up to the shoulder, where you now introduce the scapula and the clavicle and the acromion for special attachment sites as well as functional movement. And then you have the pelvic girdle, which is a huge location of attachments and origins in it. To further that example of how locomotion or leverage and support are used with the bones and the skeletal muscle, you can see here some of the origins and insertions and how the bones interact with the skeletal muscle to provide levers and axis of rotation to generate the movement of both the lower extremity and the upper extremity. Since the skeleton is a living structure, it has the ability to adapt to the stressors it is imposed upon. So according to the UofI law, which is bone remodeling, is a function of the mechanical stresses demanded or placed upon it. When there's a sufficient demand placed upon the bone, loading the bone's osteoblasts continue the process of growth and deposition. When there's a lack of load imposed on the bone, the process of bone degradation and reabsorption begins. During the lengthy periods of time, inactivity or improper nutrition, this process can lead to osteopenia or osteoporosis. It is this concept of the Wolff's Law that discusses the idea of use it or lose it within the bone formation and strength. By doing weight bearing or body weight exercises like running or cycling, you have more ability to load and produce growth as opposed to reabsorption within the bone. Let's also understand that bone is adaptable, and it's characterized as being both anisotropic and viscoelastic. Anisotropic identifies the properties of bone that respond differently in the direction of loading, as opposed to isotropic. In addition, the viscoelastic nature it responds to both the rate and the duration of loading. Whereas something has a high load but a short duration responds differently to something that has a load rate but over a long duration. And we will talk about some of those stress-strain relationships later on in the course. So the direction of loading refers to how the force or load is applied to the bone. Individual bones are designed according to the load or the location at which they are most and commonly involved with. The stress that a bone is exposed to may come in the form of compression, tension, shear, or torsion, or a combination thereof others. Stress refers to the amount of force per unit area, and we'll talk about more about stress and strain later on in the course, but it's important to talk about it from this component here as we get through the structures. Whereas strain refers to the change in length or angle of the structure as a result of that applied stressor. The direction and type of loading placed on the bone is indicative of the amount of stress the bone can withstand, as well as the duration it may withstand the applied stress. As you can see by the graph, compression, during compressive, you can withstand a greater amount of stress as opposed to shear. If you look on the images to the right, you have different components of normal strain, shear stress, normal stress, and the direction at which the force vector is being pulled or compressed. As you can see, stress is force divided by area, and strain is a change in length or angle from the original during applied stress. This concept of stiffness will come into play as we talk about the stress-strain relationship on another discussion. However, it is important that we talk about it here as well. When strength of a bone is described, it refers to the amount or the magnitude of stress the bone can sustain prior to failure. Failure is rupture or breakage. The stress is measured as a function of the direction and duration of the applied load. This value is the magnitude of the load just prior to failure. The stiffness of a material is represented by the load deformation curve in the stress-strain graph. The stiffness of a material represents the material's resistance to change in shape in response to the load being placed on it. This graph here is very important. So if you look at the graph, you'll see on the y-axis we have load, and on the x-axis we have repetition. And repetition can mean one of two things. It could mean duration of the applied load, or it can be the number of times the load is applied. Okay, and so the load, as we go vertically up, this is a greater magnitude here, and this is a smaller magnitude here. So that is the amount of load or applied. So it could be compression, tension, or shear. The component is this: as you have a greater load, you need to have a lower repetition or duration to be in this tolerance. The tolerance zone is that healthy where the structure can respond and not break. Anytime we go to the right of this line, we are now in the injury section. So the idea is to have the magic combination of load versus repetitions, duration, or amount, number of times to keep you into that tolerance zone. As we look at cartilage, there are a number of different types of cartilage. There's hyaline cartilage, fibrous, and elastic cartilage. Hyaline cartilage is also termed articular and covers the ends of the long bones at the joint surface. Fibrous or fibrocartilage that is found within some joint cavities, the intervertebral disc, and other locations. And then you have elastic cartilage, which is found in the external ear of the organs. We really won't touch on much elastic because that doesn't deal with human motion. We are typically worried about the articular hyaline and the fibrocartilage, which are involved in the idea of transitioning or transferring the force production onto the bone, into the movements, or increasing joint stability, or they are also involved in improving fit or absorption. And we'll talk a lot about that going forward. But the mechanical properties and its ability to withstand different loads are a function of the interaction of the collagen and the proteoglycan in response to the type of loading and duration and magnitude. Right, so these are the functions here. A really big one is that distribution of load in the joint, because what you don't want to have is to have the stress over that force over a small area, because then you're going to increase your ability to load or for injury. The idea is that you want to disperse and use that cartilage to disperse that force over a greater, bigger surface area, which automatically decreases the amount of stress applied. If we go forward, we talk about ligaments and tendons. And we'll just talk about ligaments here, but these are viscoelastic materials that respond differently dependent upon the stress that they are imposed on. This ability to respond differently according to the stress applied is a protective behavior that assists in the control of energy dissipation. Tendons are comprised mainly of collagen and water. However, the arrangement of the collagen fibers are different in ligaments and tendons than they are in the cartilage. Ligaments and tendons tend to have a more parallel, where ligaments are truly parallel and tendons are nearly a little bit more are nearly parallel, where they do have a little crossing of the fibers. But remember that cartilage is a matrix. And this aids in the transition of the force production through the stiff structure of the ligaments and tendons. And if you remember, the cartilage, one of the main functions of the cartilage is dissipation. And so that arrangement of that matrix allows for the force to be distributed. We're really here in the ligaments and tendons, we're trying to transfer that force along the lines. As we transition to skeletal muscle, it's important to understand that skeletal muscle is comprised of a number of properties. And these properties are related to the current state of activity or stimulation within the muscle itself. So the first one we're going to talk about is irritability. And that illustrates their ability to respond to that electrical stimuli that we know as an action potential. Secondly is the contractility, and this is the ability to generate tension through shortening or the concentric contraction following the appropriate stimuli. So remember, truly the muscle's job is to concentrically contract to generate tension and pull on the skeletal muscle to produce movement. They also have the ability to be extensibility, and these are the extension or to lengthen beyond the resting length as a protective measure given their nature. Now, it's important to understand here that the muscle doesn't actively lengthen. Oftentimes, the lengthening occurs because of a contraction or a concentric contraction of an antagonist muscle, or just through the body going through a motion. But passive, this is a passive component, but we'll talk later on where this benefits us in human movement. Finally, they are also elastic, and the elasticity allows, it's the ability of the muscle to return back to its resting state following the concentric or eccentric contraction for the shortening or elongation. So there are a number of functions also that a skeletal muscle can see, and we will begin to focus on those that are really involved in human motion. As you can see, this final one here talks about there are other non-movement related functions, and we won't focus on those, but if you want to know those, you can go ahead and search it. But for our purposes, the idea is that it produces movements, maintains posture and position, stabilizes joints, and that's really through the origin and insertions and the ability to contract and elongate in the process. We often refer to muscles as either movers or stabilizers, but this is a nomenclature that really depends on what the task is and how the movement is constructed for that number of muscles being involved. And so any muscle truly can be a stabilizer or a mover, especially the long muscles involved in the lower extremity and the upper extremity. Some of the ones in the pelvic girdle and some of the stabilizers of the spine are really stabilizers, but for the most part, a muscle can act as either a stabilizer or a mover. Further development of the musculature is the architecture. There's two major ones, parallel and pennate. But let's talk about some of the parallel first. And if you can see the parallel, the fibers run in line with each other along the prey. So the fascicles are parallel to the long axis. There are different shapes that constitute the parallel. So here you have the circular, here you have the strap. These are flat, which are some of your obliques. And then you also have the radiant or convergent, which is like a lot of your pec major, where it attaches or originates, sorry, at a big flat, and then it all converges on the insertion into the humerus. So it summates all that force being produced by individual fibers into a small location. So the functions of parallel, it favors high contraction speed and a greater range of motion. So when you look about the parallel fibers, think about high contraction velocity or speed and greater range of motion. Differently, you have the pennate fibers, and pennate fibers means that you have fibers that originate or insert into a centralized tendon prior to going on into the tendon into the muscle, or sorry, into the insertion on the bone. But they are feather-like, and then the shapes are unipennate or one pennate, bipennate, or multipennate. And here you have the different concepts. So here you have the fibers attaching to a central tendon and then elongating. Here you have the bi, which is two sets of fibers in the central tendon. And here you have the multi, which is a couple different groups, as in the deltoid, all come down to a central tendon, and then they go forward. So differently from parallel, these have a slower contraction speed and a smaller range of motion. But these ones are very, very influential in force production. So those fibers that are more worried, the quadriceps femoris, the gastroc, that are interested in greater force production are going to be the pennate style muscles. And then when we get to architecture, pennation angle means quite a bit. And so when we look at force production, and this is where your geometry comes into play, where you have your triangle and you're using the 30 degree of angle pennation. So if you have the force being produced by the tendon, which is this part that attaches at the angle to the bone, you have to take into account the angle of its insertion, because that is what is going to produce the pull of this direction on the fiber. So you have the fiber force, and then you have to multiply that time the cosine of the angle at which it's pennated, and that tells you how much of that fiber force is being produced into the tendon for the pull, and then how much is transitioning to the pull. Now, it's very important to understand that this fiber angle can change during the process of a contraction. So it's not a permanent or dominant angle of pennation. It changes throughout the motion of the angle of where the bone is created and where the shortness or contraction length of the muscle fibers. So going further, we have a couple concepts that are really important, and this shows you the idea of where the muscle volume and why pennate muscles can produce a greater amount of force. So the first component we want to look at is going to be this concept of muscle volume. And muscle volume is simply the mass of the muscle, the density of the muscle. So mass divided by density. Okay, and then we look at this general cross-sectional area. If I was taking a muscle and just cutting it in half, so the generalized cross-sectional area is the muscle volume divided by the fiber lengths. So if I have a fiber length that's this long versus a fiber length that's this long, all right? And so if I cut them across, I'll have this diameter is the volume. If we calculate the volume in there, and then we see how long those muscle fibers are. So then we have the anatomical cross-section area, which is perpendicular to the long axis.
And so if we have a bunch of fibers coming this way, it's just boop, cut it right there, and that's our anatomical cross-section area, which is different from the physiological cross-section area. And this is a sum of the total cross-sectional areas. So if I go ahead and erase all this real quick, and I'm going to draw, give you an idea of a pennate, right? So if I have a bipennate coming down, and we have the fibers going this way, fibers coming this way, to that central tendon coming down. If I did it this way, that would be the anatomical cross-sectional area to the long axis. But the physiological is going to come this way and get perpendicular to the fibers in the plane perpendicular to the direction. Right, so you're going to get more fibers in that cross-sectional area summating the force. And again, because we're going perpendicular to the fiber plane, we have to go back to the geometry and calculate the angle at which we're talking about. Okay, so here you have the density over the fiber length, okay, and the mass the mass of the skeletal muscle that you're doing, and the angle of pull, which is the cosine theta. And this is the physiological cross-sectional area. Keep in mind now that there are many different ways that muscles attach to the bone and produce movement. They can either do it directly, they can do it via tendon, or they can do it via an aponeurosis. And this is really a component of how much force is required to transfer from the muscle to the bone in order to produce movement. You can see the long head of the triceps is the tendon because there's a greater amount of force being produced there. The force production required here, the coracobrachialis is small, so it can go directly to the bone, and the aponeurosis is a smaller force production that expands out to multiple bones, so that allows the force to be distributed on multiple bones along the process. So another component is that musculotendinous junction. This is where the myofibrils join the collagen, producing a multi-layer interface. This is absorption and generation of tension, and the tendons are in series. So this musculotendinous junction is right here, the moment where the gastroc meets the tendon. So it's right at that point where you have that transfer of force production at the gastroc into the Achilles tendon that is going to transfer. Also, there's the ability where you have the tension created at the gastroc coming up, or sorry, the Achilles to the gastroc, and there's that absorption in the Achilles that creates it. So the mechanical stresses on the tendon of the quantity of force. There's a speed of muscle action that transfers, and this is part of that viscoelastic nature. And then if there's some slack in the tendon, depending on the position of the foot, the Achilles tendon is put through different stresses and different strains based off of its position. If I'm in a plantar flex position, then the Achilles is much more relaxed and it's not as taut. If I go through dorsiflexion, all of a sudden that Achilles becomes very tight with the elongation. Furthermore, this is a location of quite a few injury sites, and that's because of the concept between the muscle belly and the musculotendinous junction. Those are two locations depending on how fast the rate is. If it's a slower rate, it's the tendon bone junction. If the tension or is created at a very fast rate, the tendon is tended to fail first, right? So if it's a slower rate, the tendon bone junction. If there's a tension at a fast rate, it's going to be at the tendon itself, not at the junction. So if we look back at muscle, tendon, and bone, which we just went over, we kind of talk about how their stiffness models portray. You can see that bone is a stiffer material, and you can tell this based off the slope of the stress strain curve right here. This is a very steep slope as opposed to the muscle, which is more shallow. So of the three, muscle, tendon, and bone, we would say that muscle is more compliant, tendon is more in the middle, and bone has a more stiff component to it. What that means is with the different amounts of stress, muscle will have a greater change in length and bone will have a smaller change in length. Okay. But also what we can see is that bone it tends to be a break at a much smaller stress than tendon would, or that muscle would. Muscle may be able to endure a greater stress before it breaks or fails. So as we go forward to the neuromuscular component, there's some sensory receptors in our system in the muscle and tendon proprioception that aid us in the mechanical distribution and stimulate our motor response. Two of these components are the proprioceptive components are Golgi tendon organs and muscle spindles. And you can get from the name in each of them where they're located. GTOs are in the musculotendinous junction, and they monitor force or tension within a muscle. And muscle spindles are within the belly, and those are responsive to stretching. So Golgi tendons are responsible to the greatest amount of tension or smallest amount of tension, and they will inhibit or produce a response if the tension is created too much. Where muscle spindles, if it's something is stretched too much or the rate of stretching, so this is also a rate of stretch dependent, the muscle fibers will then produce the antagonist muscle through the neuromuscular system and the afferent efferent loop back to the central nervous system to contract the antagonist and withdraw from the motion. And these are meant to be protective mechanisms within our system, more of a reflex mechanism as opposed to a long loop, closed loop system. So if we look at the neuromuscular or neurological components, we have to first talk about a motor unit. And a motor unit, it refers to the motor nerve cell and all the muscle fibers that it innervates. And this can range from 5 to 2,000 motor skeletal muscles, depending on whether it's a gross or fine motor control. So something that has fine motor control, like your hands or your eyes, then you have more towards that range of 5, the smaller, because you need more control. Something with gross, like a quadriceps, which is really involved in force production, and greater movement can be upwards of the higher range of that. So when we do this, we talk about innervation ratio, and what that is the number of fibers that are controlled by one neuron. And we just talked about the benefit of having a lower number of fibers innervated per neuron, and that is going to be the idea of being able to have more control because that motor neuron controls fewer muscle fibers. Here's a quick depiction of the interaction between the nerve extending from the spinal cord of the afferent neuron, connecting with the muscle fiber at the dendrites. And it shows, if you look at the gastroc here and cortical brachioradialis, you'll see that the dendrites branch out and connect at the axon terminal with multiple muscle fibers at each the gastroc and the upper arm motion. Here you see where two motor neurons come out and attach to different muscle fibers within the same muscle belly. So multiple motor units will be in charge of doing multiple muscle fibers within the huge muscle. But those dendrites create these neuromuscular junctions, and this is where at the axon terminal and the synaptic cleft, you'll have the action potentials created, and the myosin and actin create down here in the myofibril, they create the individual cross-bridging that creates a concentric contraction and going in towards creating the force. And we'll go over a little bit more of that later, but if you haven't looked at the activation of a muscle contraction or skeletal muscle contraction with concentric contraction and the steps that do that, I would suggest that you go ahead and review that and see where the force production is being occurred. So going forward, there's in the neurological component of it, in the motor units aspect, there are nerve cells and motor neurons that have different characteristics to it, and these are all different characteristics that include force production. So for our purposes, we're going to go very simplistic with this. Truly, there's a continuum with type 1 over here and type the fast twitch glycolytic over here, and there's some continuum at which we can go back and forth to a certain extent and create capacities or characteristics of the other ones. And we won't talk that in this class, but understand there is a continuum of muscle fibers and or motor neurons that have the ability to take on characteristics of the other ones. What you have to understand, and what I want you to know for this class, is that the type slow twitch produce a lower force level, but they have they're very fatigue resistant, right? So they have a slow fatigability or slow fatiguing characteristic to them. And as you move more towards the fast twitch glycolytic, you become increase in your force production, but you also increase in your fatigability. And so the type 2B or type 2X or the fast twitch glycolytic, depending on what you refer to it as, are fast fatigable, where these 2A, these kind of intermediate fibers, oxidative, fast twitch, tend to be fatigue resistant, but they do fatigue quite a bit, right? So that is another component of it. So we call this the size principle as we go forward, and it means small, large, and larger is the order of which the activation and sequencing based on the threshold of excitation. So small get recruited first because they have a slower threshold to be activated, larger and then large and then larger, depending on that threshold of excitation. And so what you can see here is as the intensity increases, that means that the demand or to increase force production is also increased, or the ability to activate more percentage of the muscle fibers increases. Then we transition, we make the jump up from slow to faster or fast twitch glycolytic. So this size principle means that there is a step ladder of when these are activated, and it starts with the small to the large to the larger, or type 1, type 2A, type 2B, whatever your nomenclature is going to be. So one of the things we talked about going back to the neuromuscular junction is that they produce an action potential which stimulates the concentric contraction. One action potential is this twitch. So you'll have a single increase in force production, drops back down, and that is just one action potential coming through. And here you have the electrical activity component, and then you have your twitch and force production. Now what happens is the way this works is that if I need to produce a certain amount of force, I get a twitch, and then I want to activate more, so I get another twitch, and then we do this thing called summation, and you're summating these twitches because what doesn't happen is there has to be a time component that allows that first twitch to come back down. If the time between those twitches is short enough, then you have a summation, and the action potential or the electrical impulse from the next twitch summates on top, and so you get an increase in force production because now I'm increasing the amounts of myosin and actin and myofibrils that are being activated to produce that force. What happens is you continue to summate as your frequency of action potentials increases until you reach the state of tetanus. And tetanus is where you are at your maximum contraction and force production in that muscle. And so all the maximal interactions between myosin and actin are there, and there's no breakage in the electrical impulses, allowing the time for this unfused tetanus to where you keep dropping down. So this shows you the difference between a twitch versus a summation of twitches versus that ultimate tetanus. And in this graph on the right hand side, the unfused tetanus is that same location of the summation, and it shows you how you reach a particular force production and it goes down because there's time in between the individual electrical impulses. Well, how do we measure those
twitches in the force production. And I kind of showed it to you earlier where it said action potential, but this is a concept of electromyography, or EMG. And this is a surface, typically a surface, most commonly. Sometimes we have indwellings nowadays too, where you can go inside the muscle. But it's measuring that action potential, or the electrical change, discharge, voltage, positive to negative or negative to positive, of the skeletal muscle that it's looking at. And so the action potential is truly changing the currents of the myofibrils and skeletal muscle sarcomere that create these action potentials. So a motor unit action potential, a MUOP, is electrical signal that's generated from the muscle fiber in response to the recruitment. And this positive and negatives that change in membrane potential, which actually you're measuring and you're reporting. So it's important to understand that EMG is a measure that we can use, but it has many different factors that affect the signal. These are a few of them here: the rate of tension buildup, your fatigue, the reflex activity, and the lengthening or shortening of the muscle. Also, what we're doing is, since we're measuring oftentimes on the surface, the level of adipose tissue, or the level of interference between the electrode and the skin surface itself, can affect that signal as well. The most important aspect for you to remember is, yes, although we can assume and we have seen that with increased EMG activity, that shows us an increase in the force being produced by that skeletal muscle, it's important to understand that this is not a linear relationship. For every given increase in muscle force produced, we don't see that same increase or a linear trend increase in EMG activity. So we know that in a isometric contraction, we tend to see the greatest amount of force produced and EMG activity that's excitable. But as we take and go in smaller increments of that force production, we don't see the same decreases or increases in EMG activity per unit. So this is going to be something very important for you to understand. There's no linear relationship between the amplitude of the EMG signals and the muscle force produced.